How did the universe come to exist? At present, the Big Bang Theory is widely accepted by physicists. But how do physicists prove that the universe was created in the Big Bang? According to some philosophers, the universe has no boundaries in space and no beginning and no end in time. Even Albert Einstein thought that the universe was static at that time. To prove that the universe was static, Einstein added the cosmic constant A to the gravitational field equation of general relativity. This is because when the equation was first solved for the whole universe without the cosmic constant lambda, Einstein found that this equation led to an expanding universe. This went against his beliefs, and he felt it must be wrong. He added the cosmic constant just so that the universe wouldn't expand from the equation, so that he could get a static universe. At that time, in 1922, Soviet physicist Alexander Friedman calculated that the static universe is an unstable equilibrium. It is like a pin on a table with the tip of the pin on the table. If there is a slight disturbance, it will fall immediately. Such a static universe is meaningless. Friedman then removed the cosmic constants from Einstein's original equations. After repeated calculations, he arrived at a pulsating model of the universe, a model of alternating expansion and contraction. Einstein thought that Friedman's work was wrong. He thought that he had solved the problem of the shape of the universe and that the state of the universe did not change with time. So he suggested that the journal not publish the paper. Friedman had to submit his paper to a small German mathematics journal. The journal had little influence in the physical and astronomical world. So although Friedman's work was published, it was not recognized by his peers. In 1929, the American astronomer Hubble had a world-changing moment. At that time, Hubble made a systematic observation of the galaxies in the vast expanse of space beyond the Milky Way. He found that the spectrum of light emitted by these distant galaxies had a distinct redshift. A redshift means that the wavelength of a wave becomes longer and its frequency decreases. The frequency of a wave decreases, and we can see this in our lives. We know that both light and sound waves are waves. For example, when a train is coming toward us, we may feel that the sound of the whistle is a little sharper. This is because the frequency of the sound wave is increasing. When the train is moving away from us, we feel that the sound of the whistle is duller because the frequency of the sound wave is decreasing. This is the frequency of the sound wave decreasing. Likewise, the light waves of the galactic spectrum are reddish. The redshifts in the spectra of galaxies can only mean one thing. All these distant galaxies are moving away from us. By accurately measuring the redshift in each galaxy's spectrum, Hubble found that the rate at which these galaxies are moving away from us is directly proportional to their distance from us. What Hubble discovered was the fact that the universe is expanding. Since the universe is expanding, we can immediately work backwards. The universe must have been smaller than it is now. If we go back further, the universe must have had a beginning, and in the beginning it was a very small point. This is the origin of the Big Bang Theory. Predictably, you can imagine how Einstein felt when he heard about Hubble's observations. He even went to the Wilson Observatory to see for himself. Faced with the facts, Einstein accepted the theory of the expansion of the universe. He spoke of Friedman's model of the expanding universe, which he had unjustly rejected, admitting that it was the biggest mistake he had ever made in his life. He announced that he would abandon his static model of the universe and admit that the universe was indeed expanding. In 1929, physicists painted a picture of the universe that looked like this. In the past, the universe was hotter, denser, and expanding faster. Over time, the universe became colder, less dense, and expanded less rapidly. As for the last point, slower expansion has been proven wrong by later scientists. We will discuss this point in more detail later. Now that we know the universe is expanding, Einstein was relieved to get rid of the cosmic constant, and the gravitational field equation became simpler. The equations showed that the universe was expanding, as Hubble had also observed. Now everything seems solved. But the Big Bang Theory was like opening Pandora's box. It raised a number of doubts among physicists. For example, how fast is the universe expanding? How did the Big Bang produce a multitude of stars? How did the Big Bang create particles such as electrons, protons, and atoms? Welcome to Audible Wisdom. The book we're talking about today is Astrophysics for Busy People by Neil deGrasse Tyson. The book focuses on these four main points. First, how astrophysics has figured out the origin of the universe and how it works. Second, how astrophysics discovered dark matter and dark energy, and what are the unsolved problems of dark matter. Third, the universe is like a living organism. It has a beginning and an end. Fourth, what the cosmological perspective teaches us about ourselves. The expansion rate of the universe. We know that, according to current physical discoveries, we have yet to find any object in the universe that can move faster than the speed of light. Of course, we're talking about the speed of the object itself as it travels through space. Then, which is faster, the expansion of the universe or the speed of light? In fact, the expansion speed of the universe can exceed the speed of light. At the beginning of the Big Bang, the early universe expanded faster than the speed of light. And now, those galaxies that are so far away from us are also moving away from us at a faster rate than the speed of light. And that means that those distant galaxies in the universe are moving away from us so fast, faster than the speed of light. So fast that the light they emit can never reach us, which means we can never see them. So how did physicists figure out how fast the universe was expanding? 43 years after Einstein's death, in 1998, physicists Sol Perlmutter, Brian Schmidt, and Adam Rees wanted to measure how much the expansion of the universe was slowing down. They had some particularly good targets, called Type I supernovae. It was originally a binary system. It's a binary system where one of the stars is a white dwarf. The white dwarf keeps absorbing the mass of the neighboring stars, and when its mass has grown to 1.44 times the mass of the Sun, it will suddenly explode into a supernova. The mass of the supernova is always 1.44 times the mass of the Sun, and its brightness is always the same. This allows astronomers to use Type I supernovae as a measuring stick. They can tell exactly how far away they are from Earth by how bright they are when they reach Earth. But the results came as a shock to astronomers. The actual distance of the supernovae, as measured by their brightness, was 15% greater than the distance calculated using the average rate of expansion of the universe. This means that the expansion of the universe is accelerating, not slowing down. This discovery is a real shock to the senses. However, after repeated tests by scientists, this result was confirmed to be correct. Finally, 3 scientists were awarded the 2011 Nobel Prize. Physicists had to reintroduce the cosmological constant into Einstein's equation. But this time, the numbers were changed so that the equation suggested that the universe was expanding at an accelerating rate. So what makes the universe expand at an accelerating rate? Well, it has to do with dark energy, which we'll talk about later. We will analyze it in detail later when we explain dark matter. At this point, physicists have confirmed that the universe is expanding at an accelerated rate. They have confirmed that the universe is not static. The universe was created in the Big Bang. In the past, the universe was hotter and denser. Over time, the universe has become colder, less dense, and is expanding at an accelerated rate. How the Big Bang happened. When you look up at the sky, what do you think of? You may think of the vastness of the universe and the smallness of life. The truth is that what modern physicists have discovered is much richer and more exciting than we can imagine. In the past, people thought that heaven was a place where God lived, and that there were laws in heaven that were completely different from those on Earth. But Newton's law of gravity was the first theory in history that claimed to apply not only to the Earth, but to the entire universe. This theory explains the laws that govern the behavior of celestial bodies. The heavens and the earth are equal before this law. As you can imagine, this theory was a shocking discovery for the people of that time. In the 19th century, physicists discovered that the spectrum of each chemical element has its own unique characteristics. By shining a light on a gas and looking at the spectrum of light it absorbed, physicists could accurately determine which elements were present. Using this tool, physicists immediately analyzed the spectrum of the Sun. At this point, physicists finally realized that the various elements in the Sun are basically the same as those found on Earth, which are hydrogen, carbon, oxygen, nitrogen, calcium, etc. There is only one element that is not found on Earth, helium. But there's a place for it in the periodic table, and now we can make helium on Earth. For the first time, Mankind had learned that the material that makes up the sun is not a mystery, but a common element found on Earth. Physicists analyzed the spectrum of light from distant stars and found that they were all common elements on Earth. It was a remarkable discovery. Although the scientists had never left Earth, they knew that matter in space was no different from matter on Earth. So, if aliens were to visit Earth, the flying saucer in which they were traveling would be made of common elements. And the physical laws of the universe apply to us. For example, look at two stars deep in space whose orbits are affected by gravity. If you calculate their orbits, they'll follow Newton's law of gravity. In this case, we can use the same law of physics to calculate the origin of the universe. Physicists have used astrophysical observations and calculations to show that our universe began 13.7 billion years ago. Our universe began with a Big Bang 13.7 billion years ago. The laws of physics as we know them came into play 10⁻⁻43 seconds after the Big Bang. This is known as Planck time and is the smallest time known to man. There are four basic interaction forces in physics: gravitational force, strong interaction force, weak interaction force, and electromagnetic interaction force. Before Planck time, the four interacting forces were unified. Describing this state required a physical tool that combined general relativity with quantum mechanics, a physical tool that has yet to be discovered by man. Gravity breaks free and acts on its own after 10⁻⁻43 seconds. At that time, the universe was a tiny dot with a diameter of 10 to the negative 35th power of a meter, but it was extremely hot. At 10⁻⁻35 seconds, the strong and weak interactions are separated. Later, the weak and electromagnetic interactions separate. At a trillionth of a second, there were particles in the universe, namely quarks and leptons. The electron is the most familiar lepton. At that time, there were quarks and electrons in the universe, as well as antiquarks and anti-electrons. In 2012, physicists discovered through simulations that under the extremely high temperature conditions of that time, quarks and electrons could move freely, and the universe was like a quark-lepton porridge. The main phenomenon in this porridge is the creation and annihilation of positive and negative matter. When quarks and antiquarks, electrons and anti-electrons meet, they annihilate each other, releasing two photons of very high energy. If positive and negative matter always come into existence and disappear in pairs, then why is our universe full of positive matter and not negative matter? For some reason that physicists do not yet understand, for every billion pairs of quarks and antiquarks that annihilate, one positive quark survives. Our universe today is made up of such survivors. For every billion annihilations of positive and negative matter, there is only one survivor. These survivors are very lucky. 1/1,000,000th of a second after the Big Bang had occurred, the entire universe has expanded to the size of our solar system. The temperature of the universe continues to drop. Quarks were bound together in groups of 3, forming baryons, or protons and neutrons. At this time, protons and antiprotons, neutrons and antineutrinos are constantly colliding, annihilating each other, and becoming photons. The survival rate of protons and neutrons in positive matter is also 1 in a billion. Then, 1 second after the Big Bang, the universe has already expanded to the size of a few light years. At this point, the temperature of the universe began to drop. The lower temperature caused protons and neutrons to combine to form atomic nuclei. Of these, 90% are hydrogen nuclei, and the remaining 10% are helium nuclei. The other elements are so few that they can be ignored. When the universe was 380,000 years old, the temperature continued to drop, allowing all the electrons to be captured by the nuclei, forming hydrogen and helium atoms. By the time the universe was 1 billion years old, these atoms were gravitationally bound together to form stars, which began to form galaxies. At that time, there were already 100 billion galaxies in the universe, each containing hundreds of billions of stars. Some of these stars are 10 times larger than the Sun and produce heavier elements at high temperatures and pressures. When these stars explode, the heavier elements are ejected and spread throughout the universe. That's why there are heavy elements in the universe today. Otherwise, it would be almost entirely hydrogen and helium. 9 billion years later, in an obscure place in the universe, a star, the Sun, was born. The space around the Sun is surrounded by gases made up of heavy elements. These gases slowly coalesced under the force of gravity to form the planets. One of these planets was not far from the Sun, just enough to allow the existence of liquid water, and it was the Earth. Then, by a series of coincidences, single-celled life emerged on Earth. Single-cell life evolved over a long period of time, and eventually we emerged. You may have heard the popular saying that each of us is 1 in a billion. This is because, when the sperm and egg unite, only 1 in 100 million sperm will eventually enter the egg to form a fertilized egg. We are the 1 in 100 million winners of this contest. But when we consider the origin of the universe, we realize that we're lucky in more ways than one. Every atom that makes up our bodies, every proton, neutron, and electron in every atom, is a 1 in a billion survivor of the annihilation of positive and negative matter. These atoms, in turn, magically combine to form our bodies. Isn't it a miracle that we are here in the universe? What's even more amazing than miracle is that not only do we exist, but we've turned around and made sense of the universe in which we live. You might ask, the Big Bang took place 13.7 billion years ago. What traces do physicists use to study what happened 13.7 billion years ago? Because the Big Bang not only created the universe, it also left a gift for astrophysicists to study. It is called microwave background radiation. Cosmic microwave background radiation. As we said earlier, atoms formed when the universe was 380,000 years old. Before that, the universe was too hot and too dense for photons to travel far without colliding with electrons. 380,000 years after the Big Bang, the universe had expanded enough. Photons were finally free to fly around the universe, and they continue to exist today. As the universe expanded, the energy of these photons became lower and lower. Today, their energy has been reduced 1,000 times, and they have become microwaves that spread throughout the universe. This is the cosmic microwave background radiation. In other words, how do you tell the difference between the photons produced in the Big Bang and the new photons being produced in the universe today? The answer is temperature. In 1948, American physicists Gamow, Alfvén, and Hermann first predicted the existence of the cosmic microwave background radiation. The temperature of the cosmic microwave background radiation was calculated to be 5 K. K is Kelvin, the unit of temperature. In 1965, Arno Penzias and R. W. Wilson of the Bell Telephone Laboratory in the United States wanted to use a large communications antenna for experimental research in radio astronomy. However, the experiment could not be carried out because of constant interference from a continuous noise. The noise had a wavelength of 7.35 centimeters, which corresponds to blackbody radiation at a temperature of 3.5 K. For almost a year, they tried to track and remove the noise, but nothing worked. They called Robert Henry Dick at Princeton University and described the problem. Dick immediately realized what the two young men were trying to remove was exactly what Dick's group was trying to find: the microwave background radiation left over from the Big Bang. For this discovery, Penzias and Wilson were awarded the 1978 Nobel Prize in Physics. It was a great triumph for physics. The actual calculations of the two Nobel laureates were less than twice the theoretical calculations of 3 physicists in 1948. On November 18, 1989, observations from the Cosmic Background Explorer (COBE) satellite launched from the United States of America showed that the corresponding Planck temperature of the cosmic microwave background radiation is T equals 2.735 K. In 2001, the USA launched the Cosmic Microwave Anisotropy Probe (WMAP) with higher accuracy. The temperature of the cosmic microwave background radiation was finally determined to be T equals 2.72548 K. An astronomer later drew an analogy to describe the wonder of this event. He said it was like sitting in a room and predicting that a flying saucer 50 feet in diameter would land on the White House lawn on a certain day. And on that day, a flying saucer did land on the White House lawn, but instead of 50 feet, it was 27.2 feet in diameter. We can imagine, if the cosmic microwave background radiation were undetectable today, if the laws of physics and matter were different elsewhere than in our solar system. If the spectrum of elements wasn't so simple and consistent, it would be impossible for us to understand the universe. Above, we talked about what physicists already know and what they discovered during the Big Bang. In fact, there are still things that physicists do not fully understand. For example, physicists have discovered dark matter, but they still do not fully understand how dark matter works. Dark matter and dark energy. When it comes to discovering dark matter, we have to start with the telescope. When telescopes were first invented, their magnification was very low, and they had neither military nor scientific applications. It is said that the earliest telescopes were called peep boxes because many people bought them mainly to look at their neighbors. In a sense, once the telescope was invented, astronomers were doing the same thing as peepers, except that they were curiously observing our neighboring galaxies. There may be hundreds of billions or even trillions of stars in each galaxy. Just as the planets revolve around the stars in a galaxy revolve around the center of the galaxy. And when astronomers looked at these galaxies and galaxy clusters, they found something unusual. In 1937, astronomer Fritz Zwicky took a close look at a cluster of galaxies called the harem. Hair means queen's hair. It was named because the cluster resembled the hairstyle of an Egyptian queen. Zwicky observed that outside the cluster, the galaxies rotating around the center of the cluster were going very fast, so fast that it was a little abnormal. Let's use an analogy. The Earth revolves around the Sun. Because the gravitational pull from the center of the Sun is strong enough, it can support the Earth's rotational speed. But if the Earth's rotational speed is great enough, it will escape the Sun's gravity and leave the solar system. The same is true for galaxies orbiting around the center of a cluster. Zwicky estimated the total mass of the galaxies in the harem cluster and how much gravity they could provide. He found that the gravity couldn't support the speed at which the outer galaxies were rotating. The speeds were so high that they exceeded the escape velocity, and the galaxies should have left the cluster long ago. He suggested that there must be something else inside the cluster, something we can't see, providing the extra gravity. Since then, astronomers have looked at other clusters and found the same thing in every one of them. The most plausible explanation is that there is something inside the cluster that we cannot see. Physicists call this excess gravity dark matter. Calculations show that to maintain the high rotational speeds of the galaxies out there, the total mass of dark matter would have to be 6 times greater than the total mass of the known galaxy clusters. At the moment, dark matter cannot be detected by any astronomical instrument. Physicists have hypothesized that of the 4 known interacting forces, dark matter is unlikely to be involved in any of the other 3, except for gravity. Dark matter is not just in space or deep within the Earth. It's all around us. It's everywhere on Earth. In other words, we could be in a room full of a certain kind of gas particles, or we can think of it as gas. This particle is much larger and heavier than a proton or a neutron. However, we cannot touch it, we cannot see it, and even with all kinds of advanced equipment, we cannot feel its existence at all. It can even pass through our bodies. Now physicists are going up into the sky and into the Earth to detect dark matter. They're sending special satellites into the sky. They're digging deep, deep holes in the ground. They're running collision experiments in their labs with the most powerful particle accelerators, all in the hope of finding a dark matter particle or two. But it's been more than 80 years since Zwicky's discovery in 1937. Physicists have made no breakthroughs in the study of dark matter. The discovery of dark energy is similar as we said before. In 1998, physicists Sol Perlmutter, Brian Schmidt, and Adam Rees discovered that the universe was expanding at an accelerated rate. So the physicists had to put the cosmic constant back into Einstein's equation. But this time the values were changed so that the equations showed an accelerating expansion of the universe. So here's the question again. What is the physical meaning of the cosmic constant? Physicists can't explain it now. They have to follow the tradition of naming dark matter and call it dark energy. Dark energy is a kind of repulsion in a vacuum, but the exact physical mechanism is completely unknown to us. According to the calculations of physicists, with the expansion of the universe, in another trillion years we will no longer be able to see the stars of other galaxies in the night sky, except for the stars of the Milky Way galaxy. We have talked so much about knowing about the Big Bang. So what exactly does it bring to people to think about? What the Big Bang Theory makes us think about. The Big Bang Theory gives us more than just an understanding of the universe. It also gives us a cosmological perspective. Perspective is the angle and method of looking at the problem. What is a cosmological perspective? The most intuitive point is that it makes us realize that the world does not exist because of us. Why do we say that? Let's start with the Earth. The Earth has chosen a perfect place in our solar system. We are very lucky for that. For a planet to be suitable for life, it must have liquid water. The temperature can't be too cold or too hot, and the orbit can't be too close or too far from the star. And Earth is in just such an orbit. Astronomers call these rare planets Earth-like planets. How many Earth-like planets are there in the universe? Astronomers estimate that there are at least 40 billion Earth-like planets in our galaxy alone. In our solar system, Earth is indeed very special, and the emergence of human beings as intelligent creatures is indeed a miracle. But when you look at the universe, or even just the galaxy, we humans don't seem to be special at all. The universe should not exist just for us. When we think about the expansion of the universe, we forget that there are people on this planet who are in a hurry and trying to make a living. When we follow the orbits of planets and comets, sometimes we forget our own personal triumphs and failures. Because, no matter how we imagine it, the universe is bigger than we realize. From a cosmological perspective, how do individuals live with themselves? In a museum in New York City, there's a dome movie about the universe that you can immerse yourself in. It's from a human perspective, starting from the Earth, flying out of the solar system, then out of the galaxy, and the camera goes further and further away. This gives the viewer the intuitive feeling that the universe is very, very big and the Earth is very, very small. This kind of immersive experience makes people deeply shocked and feel the insignificance of human beings. But beyond that sense of insignificance, we should also feel that we are connected to the universe. We are freer. Because the four elements that make up our life, hydrogen, oxygen, carbon, and nitrogen, are found throughout the universe. None of these elements were created on Earth. They came from the early Big Bang. They were created in a massive star. It was a stellar explosion that spread them throughout the universe. There could be an alien billions of light years away from us. You'll never meet him, but an oxygen atom in him and an oxygen atom in you were created billions of years ago in the same star. The universe is very big, but even though it's far away, if you think about the beginning of the Big Bang, every living thing in the universe has a deep origin. Another important thing about the cosmological perspective is that it humbles us. When we watch a child, we realize that the child will always make a big deal out of the little things around him or her. For example, if a toy is taken away by another child, the child yells and screams. They think that they are the center of the world, not realizing that there are much bigger things in this world than what is in front of them. What about adults? Do we have the same childish mindset? Do we also unconsciously think that we are the center of the world? We criticize others if they do not believe in the same things we do. If others do not share our political views, we want to control them. But if we have a cosmological perspective, we will realize that these differences between human beings are really insignificant. The more we know about the universe, the more we realize that our personal gains and losses, honors and disgraces, are only temporary in the grand space and time span of the universe. The cosmological perspective allows us to be more humble, to take the long view, and to be freer as human beings. Thank you for listening to Audible Wisdom. If you found this edition helpful, don't forget to share it with your family and friends. See you in the next edition.